All right, so here's the Big Bang. Here's a very interesting picture of the Big Bang. Again, it's hard to map it out. This is two-dimensional, but this is 13.8 billion years, right? And here today, this is today. We see all the galaxies pretty much spread out. Galaxies are millions of light years away. A light year is about 6 trillion miles, right? So think about 6 trillion miles. That's how many miles it is in one light year. That's how much it takes light to travel in 1 year. Now, if you go back in time, a few billion years, you see that things are closer together. And we can actually measure this. We can measure how close things were back then. And if you go even further back, you see that closer to about 12 billion years ago, we have the first stars emerge. About 400 million years after the Big Bang, you have the first stars. And then if you go all the way back to 13.8 billion, you see we're here, right? This is where all of our understanding stops. This is the Big Bang. This is exactly where all of our knowledge about the universe stops. Our physics no longer works. Relativity no longer works. We can't calculate what happens there. It's very, very difficult. We need quantum mechanics. And even with quantum mechanics, it's hard. So what was this? Well, we think it was a very hot, very dense state of all this, right? So think of all this stuff compressed into a smaller, denser, hotter state. When you compress stuff, it gets hotter. When you expand it, it gets colder. So think of all this stuff here, all the stars and galaxies in our universe today, compressed into one moment where everything was closer together. Everything was a dense state, right? Now, that's how that happened. So here's a very interesting picture of what we think was at the Big Bang itself. Like what was that state? Well, we think that it was something called a quark gluon plasma. Very, very hot. Like we're talking billions and billions of degrees. Billions of degrees. So we think the entire universe, which was the size of about a grapefruit compared to today's universe, it had a billions and billions of degrees temperature. It was super, super hot, right? And we called this a quark gluon plasma. That's where everything in the universe was smaller, hotter, and denser. In this soup of particles, soup of stuff, right? Very, very small subatomic particles in this really interesting state. At the time, all the laws of nature, they were all combined together into something called a superforce. So the weak force, the magnetic forces, all the forces of nature were combined into one. But then, as the universe expanded, the universe got warmer. It got colder, right? Because as the universe expands, you have more volume and more volume for these atoms to move in, and this made the universe colder. The average temperature of the universe got colder. And since from that state, particles began to form in terms of like the first electrons and the first protons and neutrons. About 1 microsecond after the Big Bang, the first protons and neutrons formed. And that's what gave rise to matter today. So from that primordial state, all the larger particles emerged. And then after that, about 3 minutes after the Big Bang, you have Big Bang nucleosynthesis occur, where all of the universe was a warm enough temperature. It was a prime enough temperature for fusion to begin. And what that means is all the different atoms and protons and neutrons began to fuse together and form elements like helium, lithium, and deuterium. So at the Big Bang, we see at a certain time period, certain elements were produced. And then about 5,000 years after the Big Bang, matter started to dominate. Now most of the universe, instead of being a plasma, it's now matter. It's now atoms. And then 400,000 years after the Big Bang, this is called recombination. This is when the atoms form radiation. The basically the light from this time period decouples and goes out into the atmosphere, and this is what the CMB radiation is. So here's a picture of this happening. Very interestingly, when we look out in the universe with telescopes, we see this. All around the universe, we see this. This is the entire universe in one picture. This was that radiation that was emitted, the first radiation that emitted from that time period of 400,000 years after the Big Bang. This is one of the earliest pictures of the universe we have. It's just energy. And if you take a look at it, it's actually pretty homogeneous. It looks very, very alike in all directions. That's because the universe was so small back then, and then it stretched. All points of the universe stretched apart. All points of the universe, even where you're standing. Even where you're standing. You are part of the Big Bang. Where you're standing. Because all points of space and time expanded. And the universe is now expanding faster and faster. Right, now we see the universe. Let me see here. Yep, now we see the universe getting larger and larger and larger. And what's driving the expansion is what we think is dark energy. Right? There's something within space and time itself that's ripping apart the universe, making it larger and larger. Now, the reason why we don't really see it is because gravity holds our galaxy together. So we don't see it. The expansion force is not as strong as gravity. But as the universe continues to grow bigger and bigger, eventually the universe will become colder and colder and colder. So that's how the Big Bang happened. Remember, the Big Bang happened where you're standing. The Big Bang happened right where you're standing. It happened everywhere, at all points of the universe. The entire universe was collected into that one moment where it was hotter, denser, and smaller. Okay? That's the Big Bang. Any questions on that? Black holes? What do you mean black holes? Black holes are just parts of space and time that are super dense. They're like kinks in space and time, where it's super massive. Okay? But I'm gonna go through the basics. We'll get to black holes later. I just want to get through the basics here. So that's how galaxies formed. Okay? You have about 400 million years after the Big Bang, you have a lot of that matter in the form of gas and dust. Most of that stuff in the universe was gas and dust, right? And what happens is that gas and dust can become the first stars. And here's how, and we'll go through that right now. This is how the first stars formed. So remember, like I was saying about the gas and dust all around the universe. The entire universe was full of mostly gas and dust, like hydrogen, helium, right? Deuterium, all these things. Now, what happens is sometimes these gas clouds can coalesce. They can clump together due to gravity. And here's a great idea. Here's a great picture of it. So look at all that stuff. This is all the gas from the early universe. And now look what happens. They collapse. These gas clouds collapse due to gravity. And then they form disks because of something called angular momentum. And what happens is it's like spinning your cup of coffee, right? You know what happens? Stuff forms in the center, like a vortex. Well, the same applies here. That spinning motion drove lots of material to the center of the planetary disk. And heat built up in the center. Lots of heat, right? All that heat and stuff began to make a star. The beginnings of a protostar. Here's a great image of these gas clouds and what's happening in there. But here's what it would be like to float in these gas clouds that probably the early universe was full of. It's amazing stuff, right? They're really beautiful, all kinds of colors, because the different elements in these in these clouds. Now, trying to find a great picture of it. Hold on. Perfect. Okay. So now we have a star in the center. Nuclear fusion begins in the center. And enough heat and stuff builds up in the center for nuclear fusion to begin. And what that means is if you have enough pressure, you have elements fuse together and make energy. The elements can fuse together, they knock off energy in the reaction. And what happens is the beginning of a star forms. Stars form. It pushes out material to the outwards. The outer outskirts of the disk has certain materials in there, which are the building blocks for planets. So let me see if I can find a nice photo. Here's what it looks like, right? All that debris and dust precipitates from that gas, right? Because on the outer outskirts of that, it's colder. And this allows fragments of material to clump together, become icy rocks, right? These are like your ices, right? Things like that. They clump together because of gravity, and they become larger planets. And that's how our planet formed. That's literally how our planet formed. Look at this. It's like a densing because of gravity, right? Makes all these rocks coalesce into larger fragments. And you have a lot of heat buildup. So here it is. Here's the Earth. About 4.6 billion years ago, the Earth was a molten rock, right? That just formed out of the planetary disk. Now, also during this time, a Mars-sized rock impacted the Earth. And this is how the moon formed. A giant impact produced the moon. A planet the size of Mars smashed into the Earth, and a lot of that debris went out into space. And that debris that went out into space became the moon. That's how the moon formed. A lot of that debris, this is amazing, but a lot of that debris became the moon. And then the moon began to orbit around the Earth. It went into a stable system, and now it's what we have. It's what the moon is. Okay, so now how do we get an atmosphere from this Earth, right? How do we get in oceans and stuff like that? Well, deep in the core, you have a mantle, you have iron, molten, but then you have a crust on the outer layers. The heavier material sank to the bottom and became the core, right? Your iron, your nickel, things like this. The heavier elements, they sank down because of their lower densities. Their higher densities. Higher density things sink, lower density things rise. And this allowed the crust to form on top. Now, how about the water? Where did the water come from? Well, a lot of asteroids bombarded the Earth. During this time, there was a lot of debris out in space, and this debris contained things like water, ice in the form of ice. They formed water, and this water went into the atmosphere, bombarded the Earth, and it vaporized to become an atmosphere, and then it rained down to become oceans. You have carbonate materials mixing within the oceans, making making salt water occur, more salty minerals for the oceans. You have an atmosphere form. The different pressures of the atmosphere, combined with the heat from the sun, allows for different pressure zones to develop in the atmosphere, and now you have an ocean and an early atmosphere. Now, the early atmosphere of the Earth was not oxygen. A lot of it was water vapor. A lot of it was carbon dioxide from rocks, carbonate minerals, making a carbon dioxide atmosphere. But what happens is, because the mantle, like we talked about before, the core of the Earth was still active, and it still is today very active. But back then, it was so active that it began plate tectonics. It drove apart the crust. So for example, the magma underneath the Earth, the crust, has enough pressure to uplift the crust in certain ways, right? And what happens is the crust begins to split. You get ridges. You have plates emerge. That's how plate tectonics works. The ground you're standing on right now is moving about an inch or so per year. That's because of the mantle driving this action. The mantle underneath the earth, there's a lot of activity underneath the earth driving this process. And sometimes you have magma seep up to the surface and volcanoes form. That's how volcanoes work. Volcanoes is some of that magma getting sucked up like a straw up to the surface and forms volcanic activity. And this also allows for smoke and other things like this, carbon dioxide, other gases to go into the atmosphere and make more atmospheric stuff. Now, how about life? Someone said it's all God. Okay. Yeah, so how about life, right? How did life get here? Well, now this is about 4.4 billion years ago. The Earth is full of volcanoes, very warm oceans, very warm ponds, right? The Earth is way warmer than it is today. But underground, what you have is a lot of chemical activity happening underneath the surface, under the surface of the Earth. You have a lot of uranium providing radioactivity, a heat source for early amino acids and phosphoric acids. And this is important. These amino acids, they form in the atmosphere. And we've actually done experiments on this. We take basic gases like methane, ammonia, and hydrogen, and we combine them and they make amino acids. This is how the first building blocks of life got there. They come from the earth, from the atmosphere. They form in the atmosphere. And what happens is they fall to the surface, they precipitate to the surface, and guess what? They can seep into the oceans, and the oceans is a fantastic place for chemical activity to happen. And when you have enough of these different amino acids, well, guess what? They can form certain building blocks for life, certain proteins, which become us. Now here you can see you need lots of energy. That's why in order to have life emerge, you need lots of energy. And these oceans were about maybe 150 to 200 degrees Fahrenheit. I'm sorry. 100 degrees, yes, 150 degrees to 200 degrees Fahrenheit. Just about boiling temperatures, right? And that's a lot of energy in these oceans. You also have rain, right? Now we have rain happening. Now we have precipitation on the surface. And we have ponds develop on the surface as well, where there's cooling and drying cycles, right? The sun comes, evaporation. The rain comes, it gets wet. And when you have this layer of all these different amino acids and fatty acids on the surface of the planet, they can combine together and form certain molecules given the right conditions, given these wetting and drying cycles, right? This heating and cooling cycles, right? And this is how the first protocells emerged in the oceans. You have a layer of these lipid molecules, and because of the layer it forms a sheet like this that forms a spherical structure, and this is the first protocell. This is literally the beginning of life itself. These amino acids form longer chains of peptides. These are called oligopeptides. And then these peptides can form even longer chains of polypeptides. And then sheets of amyloids. And this is what we think the first life is. But the point here is that there's a lot of activity happening in the earth. And that's why life emerged. Because of all the different chemical conditions that allowed for all these complex compounds to emerge. Quite amazing. Quite amazing. Here we have proto-RNA. This is one of the first living organisms. Living molecules. Well, molecules that allowed for life to happen, to replicate. These are certain enzymes. You have a certain arrangement of enzymes. These are just certain proteins that can develop certain genes. That's what makes up a gene. And now when you have these, RNA, these proto-RNA molecules enter into a protocell, well, now you have the early stages of life. the early stages of mitosis. And from this moment, life began to divide, multiply, replicate, and natural selection takes place. The first living organisms that really we can call life was about 4.2 billion years ago. These aren't theories, these are facts. We can observe these things, and we know to a great deal how this stuff happened. This isn't just a story. That we know that this happened for many reasons I'll get into later. Also integral for life is a magnetic field. Earth has a magnetic field that protects us from cosmic rays. And we need this because the cosmic rays can damage our genes, damage our DNA. But the Earth has generates this field because of the core's activity in the center, the movement, the motion of these heavy metals in liquid form forms a magnetic field. But the first living things lived in ponds or oceans, warm ponds and warm oceans. And over time, you have a chemical evolution of more complex organisms over time. Sugars, amino acids form. Then you've had the first DNA. Very, very complex. But RNA became DNA. Our DNA is just a more complex version of RNA, just like an advanced version of it. Okay, now about 2.9 billion years ago. Remember, this is a long, long time ago. 2.9 billion years ago. That's a long ways from today. But we have the first photosynthetic life. The first life that can use the energy of the sun to produce energy. And things like CO2 from the atmosphere. And this allowed for the first oxygen. These were called cyanobacteria, right? Bacteria is a very complex form of life, relatively speaking, to a protocell. But the point is that these are the first organisms to produce oxygen, and it fizzled up to the surface from the oceans, and it went into the atmosphere. And now the atmosphere contains lots of oxygen. And this is important because oxygen was extremely vital for living things on land. By the way, here are layers of stromatolite. These are stromatolites. These are living things. These are living bacteria in these rocks that form these structures. This is the first life that existed. Okay, now let's go into evolution now. So that's how that happened, okay? Any other questions so far? Right now we're going to go into evolution. This is a lot of information. So Okay, great. So, evolution. So, like I was talking about before, RNA molecules, they come from those amino acids, those enzymes that we talked about before. These building blocks of life mostly probably came from the Earth's atmosphere. Some perhaps came from space itself. We know that space also is an interesting place for living building blocks to emerge. But this is 4.5 billion years of evolution in one photo. This is incredible. Incredible photo. Remember, this didn't happen. This isn't like Pokemon where you have a transformation over time. This is like long periods of time and vast, many changes within these two photos and within these two things, right? These stages. But, like I said before, the first protocells about 4.3 billion years ago. And from there, we have prokaryotes. These are a more simple living, but very able to replicate living being. It's more stabilized. It also is a good catalyst for DNA. Then you have cyanobacteria about 3.5 billion years ago. That was when the first photosynthesis emerged, right? The first organisms that can make their own energy from sun and CO2. And then about 2.2 billion years ago, you have eukaryotes. These are a more advanced cell, single-celled organisms, right? These are single cells, but with more advanced features in them, like nuclei, mitochondria, cytoskeletons, and sexual reproduction. This is when the first sexual reproduction emerged, with multiple organisms being part of it, right? That's what we mean by that. Then we have more flagellates. And then we have the first animal species, about 800 million years ago. The first animal species with a mouth, with muscles, with connective tissue, nerves, photoreceptive eye spots. These are the first eyes. This is 800 million years ago. Bilateral symmetry, the first animals with symmetry, right? Where the two halves of their bodies are symmetrical. This is never before seen in life. But this emerged about 800 million years ago. And then about 600 million years ago, we have worm-like animals that resembled like worms. Then about 500 million years ago, we have the first gills, the first pharyngeal slits, right? So this is a species with some of the first gills, which enabled them to live in the oceans, breathe oxygen from the oceans. And then we have the first, about 540 million years ago, the first insect-like species resembled now the first fish-like species, the first protofish emerged, where they have spines, longer tails. And then about 525 million years ago, here we have the first brains, blood vessels, right? The ability to smell, the first noses. They emerged about 500 million years ago. And then here we have ears. The first ears emerge. More advanced eyes, a pineal gland, more advanced brains, skin layers, hearts, two-chambered hearts, more complex hearts, right? So what we're seeing here is the development of all of our organs that we have today, the organs that we inherited from these animals, from these creatures. They have the precursors to today's organs. But again, simultaneously, they all evolved simultaneously to develop what we have today. And then we have about 400 million years ago, jaws, scales, teeth, stomachs resembled more like fish, like modern day fish. Spleens, hemoglobin, the immune system, the first immune systems, right? These are more advanced creatures. And then lungs, about 400 million years ago with the first fish. Here's the first fish right here. Lungs, preliminary ribs, and other bones. Then about 375 million years ago, we have the first species with protolimbs. The first species that had the ability to at least move their arms. Like, they weren't arms like today, but they were very, very prototype arms, if you can call it that. They were prototype arms. Barely arms. And then about 300 million years ago, we have Tiktaalik, the first fish-like species that walked on land. That was the first living being on land, right? Because over many generations, it was able to walk further and further on land. Remember, during this time, the first trees emerged as well. This allowed habitats on land. This allowed these species perhaps to lay eggs on land, right? They had habitats, or perhaps they ran from predators onto land, and that's why they'd be on land. This is the first land animals to ever exist, called Tiktaalik. Amazing time. And then from there, we have amphibians evolve, more land-adapted animals, right? With complete rib cages, eyelids to protect from dirt and stuff, stronger bones, complete rib cages, and the first legs, right? Now they can walk harder and faster and stronger. And then here we have Different amphibians about 300 million years ago. This is many different things evolved during this time. After these animals went onto land, many changes happened. Land is a different habitat than ocean, right? In the ocean, there's it's a different atmosphere, different environmental pressures that would have caused these species to evolve different ways than land. Land, there's a lot more things happening around you, and you have to see further, right? When you're on land, you got to see further, and there's less water in the way, so you have to see, so you can see further, which enables you to have different types of eyes. Okay, and then from there we have the first reptiles about 300 million years ago. The first reptiles. This is where the dinosaurs emerged from. Dinosaurs split off from these first reptiles about 300 million years ago. And this is when they developed diaphragms, specialized teeth, right? Different, sharper teeth, things like that. And then after the reptiles, about 260 million years ago, the first mammals emerged, where they developed warmer blood, thicker skin, right? Lymphatic systems, erect hind legs, resembled more like mammals of today. Then they developed milk glands, sweat glands, hairy skin, four-chambered hearts, even more complex hearts, constant body temperatures, nocturnality. They lived during the night times, right? And then they would eat and hunt during the day. And then from there we have the first rodents like species. They developed. They no longer used eggs. They now had live births. Then they had marsupial pouches, nipples, placenta, things like that. And then from the rodent-like species, you have the first monkey-like species 90 million years ago. 90 million years ago with the first primitive monkey-like species. They weren't monkeys, but they resembled monkeys of today. They lived in trees. They lived in trees mostly. They had forward-facing eyes, grasping fingers, and things like that. And then about 50 million years ago, we have even more advanced monkey-like species, menstrual cycles, sinuses, claws became nails, mammaries reduced to a single pair in the chest. Instead of having multiple mammary glands, they had only two on their chest. And then Perconsul, the first ape. The first ape about 35 million years ago. A larger brain. Different chirochromatic vision. They can see multiple colors. A larger brain. Their tails are gone. They lost their tails because they began to walk further on 2 feet. Further and further. Then 15 million years ago, even more advanced apes. Flexible wrists, shoulder blades, wide rib cage, stiff lower spine. And then about 6 million years ago, we have the first Australopithecus ardipithecus. This is one of the first human ancestors, much like Lucy, right? It was bipedal. It mostly stood upright. It walked on its feet most of the time, but it still had grasping feet. They probably lived in trees for much of the time as well, though. Their brain size began to enlarge. They used tools. They began to use tools. And now we have Lucy right here, completely bipedal, walked always on her feet. And then 2 million years ago, with Homo erectus, we have clothing begin, right? We invented clothing. We invented fire. Well, we discovered fire. We constructed the wheel. And this allowed us to become even more advanced and migrate across the world. And then about 300,000 years ago, our ancestors were Neanderthals. Here's one species. Their brain size stabilizes. They have a reduction in body hair, protruding nose, brows, snout, smaller teeth, smaller jaws, and they used tools for hunting, things like that. And now here we are today, Homo sapiens. About 100,000 years ago, about 200,000 years ago was the first really Homo sapiens of today. And evolution's still happening. Always will continue to happen. But that's our story. 4.5 billion years compressed into one picture. And remember, evolution happens in a tree, right? This Evolution never stops. It's always happening, right? As long as you're replicating, as long as you're alive, you're evolving. Because mutations, why we evolve is because we mutate. Our genes can mutate. They can change. There's changes in our DNA. And when I have kids, they adopt these genes and they become different, slightly different from them, further and further, and so forth. But the point is that think of life like a tree. All of life stems from a common ancestor. And think of it like an ever-branching tree, where you have bacteria branch out to one branch, archaea, one branch, eukaryotes, plants to one branch, fungi, protosomes, armored fish, right? Echinoderms, fish, amphibians, reptiles, birds, mammals, and then humans, right? All these species up here, these modern day species, all share common ancestry right here. Everything shares common ancestry. And this is what evolution means. Evolution is like an ever-growing thread of species. It never stops. And it's never stopped since 4 billion years ago. We're alive today because our ancestors didn't go extinct. We're alive today because our ancestors didn't go extinct. That's amazing. So we started this is where humans started, right? Near Kenya. Many species humans went this way, some went that way. And some went this way, to Saudi Arabia, to modern day Saudi Arabia. There was land there at the time. It was during an ice age, and they moved all the way into Asia, Southeast Asia. Remember, there was land here because of the different ice ages. Some humans went northern, and they went into Eurasia, right? Modern day Mongolia, Asia, India, places like that. Some went to modern day China, Siberia, the Arctic, right? Some went to the Arctic. Some went into Europe. Some people went into Europe. Spain, modern day UK. And then some from Siberia and northeastern Asia, because of the land bridge here connecting modern day Russia to Alaska, they were able to walk across into the modern day North America, and they made their way down south into Mexico and Central America and South America, right? And this is where the Mayans began. This is the Mayan ancestors about 10,000 years ago. That's why there is Mayans. That's why they developed a civilization there. And there were many civilizations about 10, 12,000 years ago since then. Many wars, many fights, many battles, many countries, many nations. So much history. This is when the first writings began, right? The first religions, the first written religions begin, the first languages, the first written languages, the first books, right, emerge. So much history. So many changes in the last 10,000 years. But yeah, that's our story, guys. That's how we got here. That's incredible to me, at least. What about Adam? There was no Adam. That's our story. Yeah, that's our story. There's so much amazing stuff to learn about the world. So much amazingness. Yeah, reality is amazing. Reality is so amazing. Yeah, it's fascinating. It's incredible to just fathom what we are and what we're capable of, right? Let's take a look at the scale of the universe. Let's take a look at the scale. This is even more mind-boggling. How big the universe is and our place in the universe. There's a person. Let's zoom out. Here's a city. There's California in America. There's the Earth, getting smaller and smaller. Now it's just a little dot. There's the moon's orbit. Now we're in space, deep space, 10 million kilometers away. Asteroid belt. There's the sun. There's Venus, Mercury, all the orbits of the inner planets. Jupiter begins to come in range. Right? The asteroids are between us and Jupiter. Saturn, Pluto. These are our furthest away satellites and probes. The sun. Now the sun. A sun has an outer Oort cloud that surrounds it by about 1 light year. The sun has a very large heliosphere which traps in everything. It's hard to escape the sun. You need to be at a certain velocity to escape the sun's atmosphere. But we're really, literally, we are technically within the sun's atmosphere right now. Everything is from about 1 light year. But now, if you go far enough away, about 100 light years away, the sun fades into nothingness. It becomes another star. And here are all the other stars around us, right? There's clusters of stars around us. Here's the Milky Way galaxy. There's our galaxy. We are right there, right? On the outer skirts of a galaxy. And in this galaxy, there's about 300 billion stars. 300 billion other suns in this one galaxy. And in the center is a black hole. Lots of stars in the center, collected towards the center because of gravity. But there it is. That's our galaxy. And there's other moon galaxies beside it. And now each one of these dots now is an entire galaxy. Here's Andromeda, about 10 million light years away, or about 5 million light years away. Right? Each one of these dots is a galaxy. Oh my gosh, look at this. Clusters of galaxies. Webs of galaxies. This is amazing. Each one of these dots is an entire galaxy full of billions and billions of stars. And there could be trillions of galaxies out there in the universe. Trillions of galaxies. At least. There could be even more than that. There could be even more than that. But look at how big the universe is compared to us. Look at how large the universe is compared to our planet. All right, but let's zoom in. Here we see the galaxies. And we're on the outer edge of the galaxy, not in any particular position. Just another star. Another planet around another star. And there we are, back home. Our Earth, the only planet we know that has life. There's a person. Remember our journey, right? The person took. We are the products of 4 billion years of evolution. But let's look inside. What are we made of? Let's see. Let's go into the eye. Oh, we got a retina. We got some blood vessels in the eye. Tiny blood cells. That's what your blood is made of. Your blood is made of all these different blood cells distributing oxygen throughout your body, keeping you alive, right? That's what your blood does. Blood is what streams all your oxygen and all these nutrients and minerals to your cells to make them function. That's how you're alive. That's why you're alive. Now we take a look at one cell. We go deep into the core of a cell. We have chromosomes. These are strands of DNA combined into a chromosome. And now here is one DNA strand right here. There it is. That's DNA right there. It's nothing special. It's a molecule. It's quite remarkable, but it's a molecule made of many atoms, right? It's just a long chain of atoms, a long chain of molecules, and those molecules are made of atoms. But there it is. Now these are individual atoms right here. Now we go deeper into an atom. We see electrons orbiting around in a cloud. They have different spins, different states. And when we go deeper and deeper on the small level, things become very different. Things operate differently here in this realm. Neutrons, protons, that's makes up the nucleus of an atom. And quarks is what makes up protons and neutrons. The smallest particles we know of are quarks. But could there be something deeper? Maybe. There could be something deeper. We just can't see it. We just don't know what's there. There's so much mystery. But there's an entire universe inside of us as well. Not only is there a universe outside of us, but inside of us as well, there's a universe with all kinds of stuff happening. This is remarkable, guys. This is real. The beautiful thing about science is that it's real. It's real. It's not a fantasy. It's not mythology. This is something we can really tangibly understand and observe. That's what makes science so much more amazing than any religion. Because it's fucking real. And there's so much out there to learn about. But yeah, there could be life on Europa. Here's some different moons in our solar system. Here's just the size of some stuff. Very interesting perspective. Here's Titan, a moon of Saturn. Titan actually has an atmosphere. In fact, Titan's atmosphere is bigger than our atmosphere. It even has liquid on the surface in the form of methane. It's not water. It's too cold for water to form liquid there. But the point is that Titan is one of the best candidates for life in our solar system. It's a moon. It's not even a planet. It's a moon. But there could be an ocean of water underneath it. There could be methane. There could be living things in the methane on the surface. Here's Mars. Mars is now red because something called iron oxide. It's rusting. Because Mars contains lots of iron on its surface. And we know that in the past, Mars was covered in water. Think of it. Mars, our nearest neighbor, was covered in liquid water, oceans of water. And what happens is, over time, that water eats away at the iron mineral on the surface, right? And that's what makes it redder, because that's rust. Rust is red because iron interacts with oxygen. Water has oxygen, so that oxygen is going to bond with the iron and chemically react and form rust. And that's why Mars is rusted, because of its watery past. Mars also has poles, 2 poles full of water. Right now, there's still water on Mars today. There's still, in fact, if we melted all the water on Mars, all the ice, it's in the ice, right? It's in subsurface ice. It's also in the polar ice. But if we melted all the ice on Mars, it would cover the entire planet in about 1 meter of water. That's quite a bit of water right there. That's quite a bit of water. That's enough to flood an entire country on Earth. Venus. Venus is a very hot world. Venus is about 900 degrees Fahrenheit on its surface. Not just because it's closer to the sun than Earth, right? It's a bit closer to the sun, but more importantly, because Venus has a very large atmosphere which contains lots of CO2 gases. And these gases can trap heat from the atmosphere, from the sun, and makes the surface of Venus a boiling place. Because it traps all that heat like a blanket, right? Imagine covering a blanket on a planet. All that heat from the sun is gonna stay inside the surface, stay near the surface, and warm up the planet. That's why it's so hot in Venus. It's hot enough to melt lead, turn lead into liquid. And here's the Earth. Earth is a very interesting place. It has water, it has land, and life. The only place we know that has life yet. Here's an exoplanet. These are planets outside of our solar system that we can see. We've seen about 5,000 already. Here's Neptune. Very large, gassy planet. Very cold planet. Here's Uranus. And Saturn. Saturn has rings that are visible. The reason why is because there's lots of ice and material in form of rocks on the surrounding it. The gravity of Saturn is configured in such a way that it allows for these rings to develop. And the reason why there's certain patterns is because of gravity. Gravity wants to collect things together and make certain patterns, and tracks. Some of the stuff, well, Saturn has about 60 moons, some of them larger than our moon. But it also has lots of rocky stuff the size of mountains. Big asteroids, big icy comets surrounding the planet. It's quite amazing. Jupiter, there it is, the biggest planet we know of in the solar system. It's about 100 times the size of the Earth. And there's the sun. Here's the size of the sun compared to all the planets. This is pretty accurate. The sun is about 1.5 million kilometers in size, in diameter. And the sun is just a big ball of plasma. That's literally what it is. It's a big ball of stuff in the form of plasma, hydrogen, helium, carbon. That's what the star's made of. That's what our sun's made of. And that's what burns a lot of the stuff inside of it. All those atoms, all that pressure, all that heat fuses those elements together and produces energy. And stars can be even bigger than our sun. Our sun's a mediocre star, but there's even larger ones. There's red giants. Look how big these guys are. Here's a black hole at the center of our galaxy. It's about the size of the sun. It's about the size of a large star, but it has the mass of billions of stars. Millions of stars. Right? That's what a black hole is. A black hole is an object the size of a large star, but it has the mass. It's a very dense object. That's why it's black, because even light can't escape its gravity. It has so much gravity that light can't escape. It even sucks in light. Stars get even larger. These are stars that are hundreds of millions of kilometers wide. And these are typically stars that are about to go supernova. These are stars that are typically about to explode. They become large, and they explode in violent explosions. Wow, they even get even bigger. This is one of the largest stars we know of, Stephenson 218. A massive, massive star. 3 billion kilometers. That's amazing. Supermassive black holes. Here's nebula clouds. These are stars that died. This is what happens when a star dies. A lot of the gases and plasma from the sun, they slowly get stripped away out into space in a circular motion. And they form these clouds, these beautiful clouds that are colorful because of the different elements that make them up, right? So certain elements produce certain colors because they reflect certain spectrum or certain frequencies of light. And this is where stars begin. In the clouds, in these big giant clouds. These are called stellar nurseries. This is where stars are born, right? This is where all those disks, like where I talked about at the beginning, the planetary disks, that's where these form. That's where these are made, in these big clouds of dust. And here we have stars beginning to emerge, right? Protostars here, baby stars. Here's some galaxies, right? These are clusters of stars, right? If you have enough stars, you have a galaxy form. Galaxies are big boys. 50,000 light years across. It's around the size of ours. Our Milky Way is about 60, 70,000 light years across. 100,000 light years across. Andromeda, 200,000. It's a bigger galaxy than us. Then we have hypergalaxies, even larger, like super large clusters of galaxies. Stars. And there it is. The entire known universe. 93 billion light years across. 90 billion light years. That's amazing. How do we know the whole universe looks like that? Well, because we can see it. We can look at telescopes and we can see in microwave form, right? We don't see things in visible light because the light is too low of a frequency for our eyes to see. We need telescopes to see in a specific wavelength. But it's in microwave form, and this light permeates all of space and time, and we can measure this microwave map. It's called the CMB map, right? We can look at the map of the universe in microwave form, and we can see all the different stuff, all the radiation out there. And as far as we can calculate, it's about 90 billion light years out. Now, I just want to go over this real quick, and then we'll get into questions. I want to teach you guys how we know the age of the Earth. So how do we know the Earth is 4 billion years old? How do we know the age of the Earth? Well, this is called a zircon crystal. This is a crystal that forms in the Earth's crust. And it forms in a certain way. We know that zircon crystals only form in certain conditions out of uranium. They're made of uranium atoms. And what happens is, if a crystal forms, it has a certain amount of uranium atoms inside of it, right? We know that there's no lead. Lead can't get inside of it because if it does, it wouldn't form properly. So zircon crystals are they are mostly made of uranium, entirely made of uranium. But what we know is that uranium is a very unstable element. And we know that over time, it decays. The electrons around the protons and neutrons and electrons, they can decay, they can change. The amount of electrons can change. The amount of neutrons can change and become an isotope of lead. So larger elements like uranium, right? Lots of protons and neutrons can decay into more stable elements. Isotopes called like lead, for example. And so if you can calculate, if you know how much lead, if you can take a look at these zircon crystals and measure how much lead is in these samples, well, you know how long it decayed, because the decay rate is the same for everything. It's a mathematical certainty, right? Mathematically speaking, if you have protons and neutrons, they're going to decay at certain rates. This is called the half-life. Right? So if you know the half-life of uranium and you know how much lead is in a certain sample, well, you can determine the age by realizing that a certain amount of lead tells us how long the uranium's been there. And after a while, after a certain amount of lead is found, you can determine how old that material is. And we do this with every sample on the Earth, and we see it's about 4 billion years old, 4.5 billion years old. Now, the funny thing is that we went to the moon in 1969 and we took back samples from the moon. And we can date those samples too. There are zircon crystals on the moon. And when we date the moon samples, guess what? It matches with this. 4.5 billion years old. So we can not only date the Earth's rocks, but we can date the moon rocks. And they match perfectly the same. And that tells us also we can date meteorites. Meteorites hit the Earth. We can take a look at their samples. There's zircon crystals in meteorites too. And it tells us how old they are. And we compare and contrast all these samples. And we know that the Earth and the solar system is 4.5 billion years old. It's amazing. Now, this isn't carbon dating. This is uranium dating. This is uranium lead dating, not carbon dating. Okay? By the way, there are different radiometric methods depending on the isotope and depending on the environment or conditions. But the point is that carbon dating and uranium dating, they're very reliable methods. They're mathematically proven because we know, physically speaking, that certain elements will decay in certain ratios. Okay. Questions. I saw somebody ask about water. How did water get on the Earth? Well, there's something called carbonaceous chondrites. So, in the early Earth's history, these rocks, these space rocks, so in the protoplanetary disk, what you have is water. There's water that forms inside these nebulas. Right, these clouds contain water. A lot of nebula clouds out in space, in interstellar space, they contain water in the form of water vapor. But when this water vapor becomes cold enough, it turns to ice, right? And this ice can get inside of these rocks, right? So these rocks contain cold water, right? Water in the form of ice. And when they land on the Earth, well, guess what? The Earth was hit by all these different meteorites. The Earth was hit with all these icy rocks, and after enough time, after enough bombardment, the oceans began to form. Right? There was enough water on these rocks for oceans to form. If you take a look at how much water there is on the Earth, there's actually not that much. It doesn't go that deep. If you were to take a globe of the Earth, the water would be only as thick as like an atom or two across. A very thin layer of water on the Earth's surface. It just covered a lot of it. But the point is that there was enough water in these rocks to hit the Earth, turn to water vapor in the Earth's atmosphere, then rain upon the Earth's surface as ocean. And that's how we got oceans. That's how we got it. If that's true, there would be water on the moon. Well, on the moon, water can't exist because there's no atmosphere to keep it there. Plus, gravity's small. So the Earth keeps lots of its atmosphere because of the magnetics of the gravity, right? The gravity of the Earth is strong enough to hold in that atmosphere. Also, we have a magnetic field. The moon doesn't. The moon does not have a magnetic field. And what the field does is protect us from the cosmic radiation that can strip away that water from the atmosphere as well. So on the moon, it's too cold for water to exist at all. Let alone being part of the atmosphere, right? There is no atmosphere on the moon. But again, there is water on the moon. There is actually lots of water on the moon. It's just in the form of ice under the surface and in the poles. There's actually lots of water on the moon. It's just in the form of ice. It's not liquid water, right? So again, there's a big difference between liquid and solid water. So yeah, the moon has ice, and so does Mars. That's why most planets in the solar system, if not all of them, have water. Even Jupiter, even the gassy giants, have water on them. Almost every single one has water. Maybe except for Mercury, because it's very hot there. And there's no atmosphere. But that's the point. It's amazing that water is actually a very common ingredient in the world, in the universe. Very common. We're not that special. It turns out to be. How does it rain? Rain is rain is just water in the atmosphere that precipitates. So when you have enough gas in the atmosphere, so here's the Earth's surface, right? We have lots of trees, we have lots of ocean water. What happens is the sun beams down on the ocean or the surface and evaporates a thin layer of water on the surface. So that water, those molecules get knocked off into space. They get knocked off into the atmosphere. And they get carried up into space, up into the atmosphere, and they form clouds. Right? They form clumps of this water vapor. And over time, this water vapor, if it gets cold enough, it can start condensing. And then it can start precipitating, right? If it goes up into the atmosphere at enough, because on the surface of the Earth, it's warm, right? We're warm here. But the further up you go, the colder it gets, because the heat likes to be trapped near the surface. So as it goes up, that cloud becomes colder and colder. It starts to precipitate, right? It's much like when you're opening a bottle of water from the fridge, right? When you bring it outside, when it gets warmer, what happens? It starts to condensate, right? That's the water coming out. That's what happens. Water is at a specific phase on the Earth's surface that allows it to precipitate as liquid and it drops down. When it drops down from the sky, because of gravity, it forms water drops. It goes back into the Earth's surface. It's a cycle, continuous cycle. And the water that you drink today was probably drank from all other species on the planet. The dinosaurs probably drank some of the water you're drinking. Some of the water here is likely water that the dinosaurs drank or were in their bodies. And now I'm drinking it. But yeah, the water gets recycled over time. Trees also can transpire. Trees also give off water. Trees can store water and CO2. Okay. Any questions? What are your questions? Let's hear it. Now's your time for questions. Is it true that the Earth never loses water? Yes. Well, it loses a little bit every year. But the point is that most of the water is maintained, yes, because of gravity and because of the atmosphere. Does the moon have gravity? Do things float up when dropped on the moon? Yes, the moon has gravity. It's just that the moon has about 1/6 the gravity of Earth. Earth has about, we call it 1, right? It's 1. But on the moon, it's about 0.16. So that's a sixth of our gravity. So if I were to throw a baseball on the moon, it would go 6 times further because there's 6 times less gravity. So if I were to jump on the moon, I would jump 6 times higher. If I could jump a foot or 2 feet on Earth, I can jump 12 feet on the moon. If I tried hard enough, I could do it. So yes, the moon has gravity. The moon isn't that small, it has gravity, but yeah, that's how it happens. What if we traveled to a livable exoplanet? What would life be like there? Who knows? That's a great question. What would life be like on another planet? Well, what we're finding is that many planets out there are water worlds. They are fully covered in water. Plate tectonics doesn't happen there much. It turns out that Earth is kind of a rarity in terms of planets, as far as we can see. Now, we've only seen about 5,000 planets out there, but there could be all kinds of fish-like species out there, right? Water species, aquatic species. Those are probably the most common. Bacteria as well could be the most common type of species in the universe. But in terms of intelligent life, that's probably hard to come by. You need land. You need, a species like us requires land. What is your education before I listen? I have a degree in geoscience. Okay. Yeah, come on with your questions. Did I ask you never landed on another planet except for the moon? Well, we don't have to land on the planet to know what it's like. We can send rovers there. We can send satellites and probes. We've sent lots of probes out into the outer solar system. We've taken pictures of Saturn close up and Jupiter close up. We don't have to be there to know what it's like. We can look at it from far away. How do all the planets stay on axis? What do you mean? You mean like, why are they slanted like that? Well, we think that there was a lot of bombardment in the early solar system, and we think that a lot of meteorites, a lot of space rocks hit each other and made that slanting of the planets. In fact, some planets like Uranus are lopsided, and we think it's because of a massive collision in the past. But in space, there's no. See, if I were to throw a baseball on the Earth, it would slow down because of things like gravity and because of things like the atmosphere, right? But in space, there's no atmosphere and very little gravity. So things are able to be stable for much longer times in space. That's why We're spinning around the sun, but able to be like this for billions of years because there's not much friction in the way between us and the sun. There's nothing slowing us down that much. Why do we only see one side of the moon? Great question. The reason why is because the moon is tidally locked with the Earth. And what that means is that the moon doesn't spin on its own. It spins in the exact time as it does revolve around the Earth, right? So its spin is the same time as it rotates around the Earth. This is called tidal locking, and it's because of because of Earth's gravity. The moon is close enough to the Earth to be locked with it. It's gravitationally locked in a way that the spin of the moon is the same rate at which it orbits the Earth. So, yeah, it's hard to visualize, but if you kind of understand that, you understand that it's locked. Think of it like gravitationally locked. If the sun never ever explodes, will another star replace it? The sun will never explode. There's not enough gravity, or there's not enough mass for it to explode. A star, for it to explode, has to be at least 4 or 5 times larger than the sun. But when the sun dies, nothing will replace it. It will die in a slow death. It will collapse. It will become larger, but then collapse, not quite enough to explode on itself, but become a white dwarf. It will become a cold dwarf star, where it no longer produces energy or light in any significant way, but the plasma and the material that makes up the sun will be stripped away into space and form a nebula. These are called planetary nebulas. And what will be the remnants of our star system will be a cloud, a nebula cloud, a beautiful cloud of different colors. But nothing will replace us. That's it. Once we go out, that's it. And won't come back. And one by one, all the stars in the universe are going to die. Fade away. Dim out like light bulbs dimming out. Until one day, all the stars stop producing energy. There will be a point in time where all the stars in the universe stop shining. And the universe will become cold and dark forever. Does sound travel faster in space? Sound doesn't travel in space at all. Sound doesn't travel in space because sound requires a medium. The reason why I sound something to you is because my vocal cords are vibrating and air from my lungs is being pushed out in a certain way out into the air. But those sound waves are propagating from the air itself. Right? The vibrations of energy in my body are being transferred through the air as waves, sound waves, made of air molecules, right? The reason why I can hear you is because there's air molecules that are being pushed through the air into my ear, and my ear is being stimulated and rings something in my ear, and I can hear it in my brain. That is sound. Sound travels about 700 miles an hour in the air. But in the water, sound travels faster. Why? Because there's more medium. In the water, air molecules are far apart in the air, right? In the atmosphere, air molecules are far apart. But in the oceans, in water, sound molecules are closer together. They're liquid, right? Molecules are closer together. There's more stuff. There's more density there. So if I talked underwater, you guys, if you notice, it sounds weird, but it sounds faster, right? It sounds different. That's because your sound waves are propagating through the water differently than it does the air. In space, there's no medium. There's no air. There's no water. There's nothing. There's no way that my vibrations can be spread out into space. So you don't hear anything in space. Space is completely silent. Well, for the most part. Unless you're near a cloud, a dust cloud, right? You might hear some faint sounds. On Mars, the same applies. On the moon, there's no sound. On Mars, there's a little bit of atmosphere there, so you hear little muffled noises. Little muffled noises. You hear a little bit. But we're lucky on the Earth that we have an atmosphere where we can hear each other. These beautiful, we can hear music. We can hear people's voices. This is quite amazing. We're in a very small parameter of things in the universe that can hear sounds like we can. We're special in that way. Some say gravity is not a force. Is that true? Yes and no. Gravity is not a force necessarily. That's what Newton followed. That's what Newton said. And his laws work. Newton's laws of gravity work. But there's a limit to what they apply to, right? Newton's gravitational laws only apply to large objects in the universe. They don't really apply to smaller things. Einstein came along and realized that gravity is not an attractive force. It's more like a bending, a warping of space and time itself. So the reason why we experience gravity is because space and time warps itself, and we're following the trajectory. They're called geodesics. We are following the geodesics of space and time itself. Very difficult to visualize, but gravity is not what it seems. There's much more to it than just an attractive force, right? But again, how you describe gravity is subjective. You can describe it any way you want to, and it'll still work. The problem is that we still don't know today what gravity really is. We still don't really know what it is. We know we know the mechanisms, and we're trying to figure it out, but we don't know with absolute certainty what it really means. We don't have all the answers, and that's quite amazing. Is it possible for a planet to leave the solar system? No. Unless it's going fast enough, which is not possible. So unless there is some kind of, something pushing it out. But the problem is the sun is big. And much like the Earth, right? Think of the Earth. The Earth has gravity. If I jumped, I can't escape the Earth's gravity unless I go fast enough, right? And that's called escape velocity. So on the Earth, you have to go about 26,000 miles an hour to escape the Earth's gravity. If you don't go that fast, you're gonna go in a rocket ship and come right back down, right? So there's a certain velocity that you have to reach to escape the Earth's atmosphere, to escape the Earth's gravity, and to go out into space. The sun also has an escape velocity, but it's even faster than the Earth's. It turns out that I believe it's about 1,000,000 miles an hour. I could be wrong. No, not 1,000,000. I think it's like 150,000 miles an hour. Something around there. So you would have to travel at about 150,000 miles an hour to get out of the sun's gravity and go into interstellar space. You have to go that speed. If you don't go that speed, you're going to go right back into the sun's gravity and go back into the solar system and keep orbiting around it. So it's difficult, but yes, it's possible to leave this. But a planet on its own, I don't think they go that fast. I think they barely go that fast to really leave the sun's gravity. How do humans know that? We can measure it. We can measure gravity. We can do physics. We can do calculations. If I built a staircase to the edge of Earth's gravity, could I escape? You needed acceleration. You have to. So yeah, that's a very interesting question. If you built the ladder, sure, it's possible to build a ladder from the sun to the moon. In fact, that's what some people are suggesting that people do. They want to build a nanotube ladder from the Earth to the moon, and it's possible to do so. But again, that's only because you're able to, do that. If you're on your own, you need a certain acceleration to leave the Earth's gravity. But yes, if you had something connecting you to the moon, you can do that. But that's very difficult to do. But if you built a staircase, you wouldn't be able to leave the Earth's gravity by just going higher, right? You would actually have to accelerate faster. Okay, I lost a lot of questions. Explain a neutron star. Very simply, a neutron star is when you have a dead star, a star that dies, and what's left of it is a neutron star. But a neutron star is interesting because it's made of neutrons, pure neutrons. There's no elements in there. It's just pure neutrons. Because think about it. Imagine a large star that's constantly compressing all this stuff, right? At the core of the very, very, very core of a star is a neutron star, a neutron core. So when the outer material of the star goes away, either in a supernova or in a nebula, you have a neutron star remain, and it's a very, very compacted thing, with very pressurized thing. In fact, they're called pulsars if they spin fast enough. They spin very, very fast, and they can emit beams of energy. Okay. What kind of material do we make a spaceship to make light year travel possible without ship burning? Well, in space, you don't burn. You only burn in the atmosphere. You can go as fast as you want and not burn up in space. It's only when you go into an atmosphere it's only when you see friction do you burn up. By the way, you can't burn in space either, even if you wanted to, because there's no oxygen there. But the point is that I believe the material we use to go to space is some kind of carbon composite, I believe, like a steel-like composite. I'm not too sure, but go learn. Can you explain how the sun does not hold all the planets in tow by gravity? What do you mean? Is the sun burning helium, needing no fire? Yeah, the sun doesn't burn. The sun isn't burning like a fire. There's no combustion in the sun. The sun is fusing helium. Well, not helium, but hydrogen mostly. The sun is burning hydrogen. Two hydrogen atoms fuse together, and in the process they yield energy in the form of radiation. Ultraviolet light, right? Gamma rays, right? All these things emerge from the sun and go out into space and become us, and go to us, go to Earth. Do you think humans will ever be able to see past the event horizon? You mean the universe's event horizon? No, it's impossible. There's a certain part of the universe that will always be inaccessible to us. We'll never be able to see, because the universe is expanding, and in some regions, the universe is expanding faster than light itself. So the light coming from those areas will never be able to traverse that space that it's trying to traverse. It will always end up out of our sight, because light is a finite speed, and the universe is expanding it infinitely fast. Well, continuously. So, yes, in fact, the event horizon will continue to enlarge. As we go further into the future, the universe will become smaller and smaller to us in terms of what we can see, because the event horizon will continue to get larger and larger. And eventually, all we will see is maybe a few galaxies. And eventually, the sky will become completely dark. And the universe will become absolute darkness, void of any activity. But we're talking Google years from now. We're talking 10 to the 1,000 years from now, right? This is a long ways in the future. Not anytime soon. Black holes.
Is that why we can't see anything until 400,000 years after the Big Bang? So the reason why we can't see anything, at 400,000 years after the Big Bang is not because of the event horizon, but because at the early universe, right, the first 400,000 years of the universe was full of a soup of particles, right? Think of a very energetic soup of particles. They weren't atoms yet. Atoms didn't exist. So the light that existed in here was just bouncing off of each other, right? It had nowhere to go. It was just bouncing off each other until about 400,000 years after the Big Bang, when atoms began to form. And that's when light was able to pass the soup of particles, right? Think of it like a fog, right? Think of the universe like a foggy place in its early past. And then once atoms formed, you have that fog go away. It clears up. And the light was able to now escape out into the universe. So the light we see from the CMB is the light from the Big Bang itself. But it was emitted in infrared form, but since the universe expanded, the light stretched with the stretching of space-time. So the light wavelength has stretched into microwave form. It used to be higher energy, but now it's lower energy because of the stretching of space-time. So what we see is microwave, but it was at a different energy state back then. Much more higher energy state. Dark energy propels space-time apart faster than light can travel. In some regions, yes. The further away you go from us, the faster and faster space-time stretches away from us. Very difficult to visualize. But the space and time around us is not stretching that fast. But space-time, 50 billion light years away from us, across the universe, that space-time is stretching faster than light. Faster than light. See, you might be confused. Oh, I thought you couldn't go faster than light. Well, that only pertains to things within space-time, not to space-time itself. Space and time itself has no boundaries. There might not be no boundaries to it. It might go on forever, and it can be as fast as it wants to. But things within space-time are limited to the speed of light. And by the way, this is going to sound crazy, but everything in the universe travels at the speed of light. But there's a caveat. That speed is either in your time dimension or in your space dimension. Right? There's 4 dimensions, 3 is space, 1 in time. Your motion through space-time, if some of it is in space, most of it's in time, well, you're traveling you're traveling very fast in terms of light, right? That's like almost near light speed. But if all of your motion is in time, you're static. All of our motion is in time right now. Almost all of our motion is in time. We're moving around the sun, we're moving around the earth, but relative to other things, our motion is almost completely through time. So our speed, relative to the speed of light, is going to be slower. But the point is that all objects in the universe have motion at the speed of light. It's just that some are moving faster through time, some are moving faster through space. Very interesting stuff right there. That should change the way you see space-time. Very, very different than it seems. Does the moon accelerate when passing in front of the Earth? Yes, there are the moon's orbit is not perfect. It's not a perfect sphere, but again, the variations are very small. The Earth accelerates. The Earth accelerates in places during January. In January, the Earth is closest to the sun. by millions of miles. So that's why winter, right, in the southern hemisphere especially, is that way. Or our experience of winter seems to be shorter than summer and the fall. Okay. What if I went into a black hole? You would die. We don't know what happens inside of a black hole, but what we know is that gravity, black holes have lots of gravity. And in that sense, time seems to slow down near a black hole. Time gets weird. In fact, we think that inside of a black hole, time itself stops. The passing of time stops. Relative to somebody observing. Right? Again, remember guys, time is relative. If you were inside of a black hole, you would perceive things the way that you do right now, but from an observer on Earth looking at a telescope, they would see you as stopping in you would be in slow motion. You would literally be stopped in time relative to somebody on Earth. That's freaky. Think about that. This really happens. Time literally stops for somebody near a black hole relative to somebody on Earth. That's remarkable. Because gravity does that. Very difficult to perceive. But once you learn physics, you realize that really happens. It's really crazy. But we don't know what happens inside of a black hole for sure. We think that the energy is there, but we don't know what happens to it. There could be some other region beyond a black hole where you go into another part of the universe. So mysterious. It's possible though. Could there be other universes with different laws of physics? Sure, there could be, but there's no evidence of them. There are many ideas for multiverses. There's many different types of multiverses. There's not just one. It's not just one model. But it's not even really a model. It's really a hypothesis at best. And we'll never be able to observe it. We don't think we will, but maybe one day we will, which would be interesting to see. Which part of the visual universe can be reached in 100 years going the speed of light? So we can't go the speed of light. It's not possible for something with mass to go the speed of light, because in order for me to go the speed of light, I would need an infinite amount of energy to reach that speed. Well, I would need more energy than the universe has to go that fast. But I can reach 99% of it. And going that fast for 100 years will get me 100 light years away, which would get me to maybe a few stars away. The universe is big, guys. Even going at the speed of light across the universe, it would take you billions of years. Guys, even going across the galaxy would take you hundreds of thousands of years. Going the speed of light. The speed of light. The universe is massive. So interstellar travel is far ways ahead of us. Far ways ahead of us. But there might be an easier way. Maybe wormholes. Maybe there is a shortcut. Maybe there is a way to shortcut through the universe and traverse it faster than the speed of light. Maybe. It's possible. What would happen if the moon got closer to the Earth? It was. About 4 billion years ago, the Earth was much closer to the Earth than it is today. In fact, the moon was so close to the Earth that even ponds in lakes had tides. Even small ponds had tides. Dramatic tides. the ocean tides were way stronger. Like, we're talking, like, not just a few feet, but we're talking, like, hundreds of feet. So, back then, the tides were much stronger. So, if the moon was closer to the Earth, we would experience a brighter night, right? More light from this moon being reflected. A brighter night. We would see more tidal forces. Ocean tides would be much stronger. We'd also see more friction from the tidal friction, stretching, earthquakes perhaps, stretching of the crust. But again, these are just, we wouldn't go extinct, but it would be a very different planet, slightly different planet. What causes ocean tides? The moon and the sun. Well, the sun has a small effect on it, but the moon mostly. The moon tugs at the Earth, right? So here's a visual for it. It's hard to not visualize things. I don't know, that's how I learned, but so here's a good picture. So here's the moon. So here's the moon and here's the Earth, right? The moon pulls on the Earth. It tugs on the Earth with its gravity, right? The moon has gravity. It's a tug on the Earth. So what happens is the moon is pulling water on the surface of the Earth towards the moon. So what happens is you have a pulling this way, right? Now on this side, it's a low tide here because the water is being pulled this way. Less the water decreases here and decreases on the sides, right? Because it's pulling it like that. It's like pulling it. It's like sucking it up, right? So these sides are going to be very low tides. And the other side of the Earth is going to be a low tide as well, not as low. But the point is that's what a high tide is. It's when the moon pulls on the water of the Earth. It's tugging on it. And the sun also has an effect there, but the moon is mostly the thing that causes it. It's amazing stuff. Is Antarctica bigger than the moon? No. No, the moon is big. That's just a photo. It's not a real picture. How does a supernova completely destroy a star? So here's an animation of a supernova. What it kind of looks like. But that's all gas and dust being expelled outwards. And the reason why is because let me see if I can find a good picture here. A star is stable only because it's... Damn, this is terrible. Here's a good picture. Perfect. Okay. So if you can see this photo here. Sorry, it's so small. Damn. Okay. Well, anyway, so here is a star. In the center of a star, you have the core, right? And it's pushing out stuff, pushing out energy in the form of radiation. But you also have gravity pushing in on the star, right? The gravity wants to pull in on the star. So you have these two forces in an equilibrium, right? We have inwards pressure pushing down the star, collapsing it, but you also have outwards pressure from inside of the star, from the core pushing out radiation. So these forces combine into an equilibrium. That's why stars are stable for about 5-10 billion years. But when a star runs out of hydrogen or helium to burn, right? When all of it's exhausted and all it has is heavier elements which take more energy to burn, well, when a star runs out of all of its elements to burn, it starts to collapse again. And then when it collapses, it succumbs to gravity, right? It succumbs to gravity. The inward pressure the outward pressure decreases. Gravity succumbs to gravity. It collapses, and because it collapses, there's so much force, it explodes in itself. It explodes into a supernova, and all that stuff and energy goes out into space, into what we just saw before. So that's what keeps a star afloat, this equilibrium between these forces. And once that energy stops in the center, it explodes. Where's my mods? Like, they gotta meet these people that are just saying nonsense. Where are your studio glasses? What is little bro yipping and yapping? Wow, nobody appreciates this? Nobody appreciates learning? What are your thoughts on the moon landing conspiracy? It's stupid. We went to the moon. Get over it. What is dark matter? Dark matter is like regular matter, but it just doesn't interact with light. We can't see, it doesn't, so the reason why we can see gas and dust in space is because light reflects off of it, right? It interacts with light. Dark matter doesn't interact with light, so we can't see it directly, but we can see it indirectly because it still has gravity. Dark matter still has gravity, and we can see it happening in galaxies. We have to account for dark matter when it comes to galaxy rotation, because with all the matter that we see, all the regular baryonic matter that we see, it only accounts for a certain amount of the galaxy's rotation. We need to add in dark matter to account for why the galaxies are so fast when they rotate, on the outskirts especially. So dark matter is all around us. It's just invisible to us because it doesn't interact with light. So we just don't know what exactly it is. We just don't know exactly what it is, but we know it's there. We know it's there, which is quite amazing. What is the God particle? The God particle is a Higgs boson. And a Higgs boson is a very small subatomic particle that exists in space and time itself. In a Higgs field, it's called. And this Higgs field is like a molasses kind of thing, where particles are able to move through this Higgs field, and because of it, they gain they gain mass. The Higgs boson is what gives many particles mass. Things like electrons and protons and neutrons, to some degree. But the Higgs field is what permeates all of space and time, and Higgs boson particles are found in all space and time. And we found it by using a particle accelerator, where they take two particles, they smash them together, and it knocks off a Higgs boson. And we observed this about 10 years ago. And that confirmed that particle physics is pretty much solid. It's pretty much a solid idea. Pretty much, it's the nail in the coffin to it. It showed us that, yes, particles do gain their masses from space-time itself. So that's why it's a very fundamental particle for physics. That's why they called it the God particle, but it doesn't have to do with the actual God. How do we discover exoplanets? Great question. So exoplanets are discovered in a couple ways. Typically, we discover them through using not telescopes. We can't see them. They're too far away to see with telescopes. But, I mean, not at least directly, but we can see them when they orbit around their star. And by doing this, we can measure the light differences, right? When, for example, when the Earth passes the sun, right, somebody from the outside will see the sun get dimmer because the Earth is moving on top of it, right? Like a solar eclipse kind of thing. So if we can measure the luminosity of a star from, light years away, we can see the dimness in certain times, and we know that there's something passing around it. And if we know the luminosity normally versus the luminosity of when the planet passes around it, well, now we can determine the mass of the planet, what type of planet is orbiting around it, right? Its orbital period, things like that. So that's one way to do it. The other way to do it is by observing the gravity, the tug of the planet to the sun, right? We can measure the wobble of the star with telescopes as well. Very amazing methods, but yes, we can see them that way in many ways. We'll never see them directly, though. They're too far away, they're too dim to see directly. There's a nuclear power in a star, and the gases that normally expand are being held down by gravity. If dark matter is everywhere, how come the gravitational forces in our solar system are not affected? They are affected. Just not much. Dark matter, most of the universe isn't dark matter. It's mostly dark energy. Gravity travel faster than light. Yeah. Well, it's not that gravity travels, but space and time itself can warp faster than light, sure. Or stretch faster than light. Time was not affected by CERN. That's nonsense. When do all the planets in the solar system line up? Once a year. It happens every year. Someone just keeps saying wrong, wrong. You guys are funny. How many dimensions are there? 4 that we know of. Do you think we'll know everything? Well, the more we learn about the universe, the less we actually really know. Right? The more we learn about the universe, the less we understand that we know, the less we know that we know. Because every time you learn something, new questions arise. And you also realize how much you don't know about that thing. What's a white hole? A white hole is like the reverse of a black hole. Instead of things being pushed into the singularity, a white hole expels things from the singularity. I mean, we haven't. I don't know if we've ever observed one, but it's possible. If binary stars exist, can there be a system of 3 stars? Yeah, there can be. In fact, most stars in our galaxy are binary stars. They're binary systems. Most planets have 2 stars around them. Again, Earth is a seemingly rare thing. Most planets in our star system, in our world, have 2 stars orbiting around them, or orbiting around 2 stars. This isn't sci-fi. This is reality. We can observe these things. This is science, guys. We can observe these things. We can measure these things. We know they happen. All right. Well, who learned something today? Whose mind is blown? Raise your hand if you liked the live today. Everybody go follow my YouTube. Go to my YouTube. Follow me. If you guys want more, I'm going to post this onto YouTube tomorrow so you guys can watch again. I have lots of other science lives there too. I have my debates there on my YouTube. Go follow it. Link in my bio. The planets don't align every year. Well, from our perspective, yes, it takes a few years to align, yes. But, yeah. There's no alignment. There's no, the solar system does not align, right? So, do you believe in parallel universes? I don't know. Do solar flares affect the temperature of the Earth? No. But they do affect radio systems. So in the 1800s, there was a massive solar flare that disturbed radios from the 1800s. In fact, in Canada, a lot of their transmissions went out. They couldn't talk. And went out for a few days, actually. So that was the 1800s. Imagine getting one today. Imagine a solar flare today knocking out all of our internet. That could happen. It's scary, but it could happen. Imagine the whole world losing energy and power for weeks, even months. Do you know about Betelgeuse? Yes, there's a star out there that's about to go supernova. And it could happen within our lifetimes. Imagine if Betelgeuse explodes, it'll be almost as bright as the moon in the night sky. It'll be that bright. You can barely see it during the day, and at night you'll see even more. It could explode in our lifetimes. And there are many supernovae that happen within human. In fact, a lot of religions use that past supernovae to, make up kinds of gods and stuff. They didn't know what it was. They didn't know what those things were in the sky, right? So they said, oh, it's the gods. How big will with Betelgeuse to be relative to the moon? It'll be about, like a quarter the size of the moon, but about the same brightness as a full moon. Yeah, it'll be very bright. Everybody will notice it. Everybody on the planet will notice it. Could Betelgeuse have already exploded? Yeah, it could have already happened. It's just that it takes time for light to reach your eyes, right? Time, like I said before, is finite. Speed. It doesn't travel instantaneously. When you flick a light up in your room, it seems like it's instant, right? But because space is so big, and light travels at a finite speed, 600 trillion miles an hour. Because it travels at a finite speed, 600 million miles an hour. 600 million miles an hour. Betelgeuse, which is, I believe, maybe 100 light years away or something like that, it would take about 100 years to travel to our eyes. So even if it exploded 100 years ago, we'd just now be able to see it. Why did Mars lose its oceans? Good question. Mars lost its oceans because Mars had no atmosphere, very thin atmosphere, and because it had no magnetic field. So the sun's energy can strip away water, right? Just like think of evaporation on the Earth, right? Evaporation is the sun's energy stripping away molecules out into space, out into the atmosphere. On Mars, that same process happens, but because Mars has lower gravity and no magnetic field, well, that energy from the sun is even stronger, so it's beating down on the planet, and the molecules that get knocked off are now able to get into space easier. And after millions of years, Mars was stripped away of its atmosphere and its water. But some water seeped into the subsurface, and it became ice. Some water's in the poles. Most of the water's on the subsurface is ice. And if we melted all the ice on Mars, it would cover the entire planet at about a couple meters. So Mars retained quite a bit of its water, but a lot of it went out into space forever. Earth is a precious place, right? We're very precious here. We have the right atmosphere, the right magnetic field to survive. We have the right core to survive, the right amount of temperature and heat to survive, not thrive. There's nothing special about life itself, but we think it's special because we like it. We love life, and it's amazing. Is there life on Saturn's moon? Well, Enceladus has liquid water. Under the ice of Enceladus is liquid water, an ocean of salt water. And we know that on the surface is a thick layer of ice, about 30 miles thick of ice. And but under the ice is liquid water. And there's also hydrothermal vents in the subsurface from the core, pushing out hot stuff, hot gases. And these gases can be a perfect chemical condition for life to evolve. Life might exist on Enceladus, and we don't even know it because we'll never see it. But we can take a look at some hydrothermal vents, some plumes from these vents, from the surface. Like, a lot of that water can escape up to the surface. And if you look at Enceladus, it's amazing. Such a beautiful moon. One of my favorite structures in the solar system. But if you take a look at the surface, it has these very interesting... if you guys see them, they're like these ridges here. You guys see these like cracks? Lots of cracks. And on the surface of Enceladus is snow, water snow. Well, also carbon dioxide snow. But Enceladus is a winter wonderland. It's full of ice and snow and cold. And these cracks are from the tidal friction between Saturn tugging on it, right, cracking the ice, as well as plumes from under the surface. And these plumes can go out into space, right? And they can shoot out water, vapor. And amazingly, we actually sent out probes past Enceladus to pick up samples of this stuff. And guess what we found? We found water, methane, carbon dioxide, and amino acids. Amino acids, the building blocks of life, were found in the plumes of Enceladus. Guys, this is amazing. There could be life under the surface there. One of the best candidates for life that we know of. So, very promising that there could be something there. Europa, Enceladus, and Titan all could have life on them right now. Are they habitable? No. They're way too cold, the gravity's too small, lots of radiation. The most habitable planet we know of is Earth, except for the Earth, is Mars. Mars is the next best planet. Mars has a 24-hour day. It has good enough amount of radiation and heat. It has a decent atmosphere. Small, but okay. It has regolith on its surface. Martian dust, Martian soil is almost identical to Earth soil. In fact, we can grow stuff in Martian soil. All you have to do is add some water and, I don't know, some organics. But it's easy. It has very similar mineral content, very similar nutrient content. And perhaps one day Mars will live on Mars and grow plants on the surface or the subsurface in either domes. But Mars is the most livable planet in the foreseeable future. Eventually, we might be able to terraform it, make it something even more grander than that. Perhaps another Earth. It's possible. Hard, but possible. That we can make a twin Earth on Mars. Why is Mars red? Well, I talked about that before. Mars has lots of iron on its surface. Iron rocks. And in the past, we know that Mars was full of water. Mars was covered in water on its surface, almost entirely. And iron, when it combines with the oxygen in water, right, H2O plus iron, it chemically combines to form rust, right, iron oxide, rust. And we know rust forms on the Earth, right? If you leave a bicycle out long enough, right, if you ever had a bicycle chain, leave it out in the rain, what happens? It turns red. That's rust. So the same applies to Mars. Mars has that redness because of the rusting of the surface from the water in the past. You also have the sun beaming down and stripping away oxygen atoms from the water. That also can combine with iron on the surface. So Mars is red because of those reasons. What about the storms that happen on Mars? Yeah, Mars has windstorms. Very, very... I mean, because Mars has a very small atmosphere, the windstorms are very much less powerful than the Earth's. But there's still dust storms on the Mars and the Martian atmosphere. Because Mars has a lot of dust and a lot of sand. But I think they approach about maybe 100 miles an hour at max. On the Earth, the storms are 200, sometimes even 300 miles an hour in gusts. But on Mars, it's maxed out at like 80 miles an hour. But there's no rain on Mars. There's no rain there, at least anymore. Do you think water is needed to form life? Well, water is... See, the thing about water is that it's a very reactive compound. Water is a very interesting thing as well because water is one of the only materials that we know of that when it freezes, it expands. And when it freezes, it's less dense than its warmer counterpart. So the point is that water has certain properties that allow it to be water, liquid, solid, and gas in very interesting parameters. It also is a very reactive compound. It has H2 hydrogen and 1 oxygen. Oxygen is a very reactive element. So we know that water is a very important catalyst for life that we know of. But would it be required? I don't know. That's a good question. Probably not. It's not required, but it's very important for our type of life. But in terms of life, I think that carbon-based life is going to be the most common in the world, in the universe, because carbon is, again, a very reactive compound that enables it to build chains of itself, something that most molecules can't do. So if there's life, it's probably carbon-based like us. And probably water-based as well. I think if there's life, it's very much like going to be similar to us in structure. But there could also be all kinds of different life forms with the different materials, like silicon-based life. It's possible. It's just probably more rare. Wow, we're getting a lot of spammers. Okay, let me do something here because my mods are not doing anything. So let me But yeah, a couple more questions and I gotta go. Hopefully you guys enjoyed this. Okay, I have her as a mod. And I have you as a mod, okay. What about humanity's end goal? Do you think we'll go extinct? Well, we could. We're at a very interesting point in our history where we have lots of power but very little responsibility. We have the power to destroy ourselves. We can, start war tomorrow and the whole world will be destroyed. Climate change can affect us, right? Climate change can eventually destroy ourselves and the planet. Famine, disease, right? These things could destroy us as well. Look at the pandemic. Imagine that happened again on a grander scale. So we're at the point where we have lots of power and capabilities, but we have lots of dangers in the way. Do I think we'll make it? Yes. But there's lots of challenges that will face us that are getting increasingly harder to fix and solve. And the problem I see, the trend I see in America at least, is that people are becoming lazy in terms of science literacy. We don't understand the problems. So the problem is, will we ever be able to solve them if we don't even understand them? I don't know. But it's up to us. It's up to us. We can, if we survive the next 100 years, we can have lots of potential ahead of us. If we can solve these problems, like climate change and war, right? Things like that. If we can solve these things, we can live forever. We can keep surviving and live and go on forever. Because there's a certain point you reach where nothing else can stop you, right? Once you have enough technical powers, right? If you can feed everybody, if you can have fusion energy where you can give enough energy for everybody on the planet, well, now nothing can stop you. So if we can just reach that point, then we will survive. But getting there is the hardest thing. That's a scary thing. Do you think we'll ever be advanced to reach other galaxies? Not we. Humans are too flimsy. Our biological bodies are too weak. And our brains are too small. It's not going to be us who goes to other galaxies. It's going to be robotic life. It's going to be AI and robots. Extensions of ourselves. But we will be the first colonizers. We will be considered the first ones who went to space. Forever. Think about it. Forever, for as long as we live, our generation will be seen as the first ones who went to space. The first space colonizers. The first ones who went to the moon and Mars. So, Again, it doesn't matter if we go to galaxies. It's probably not going to happen. But what we do now in these next few decades and how we set up the next few decades is going to be vital for our future. So we got to make sure that we survive so that we can give offspring to robotic life that can do this. What does space taste like? Nothing. There's no taste to it. Taste is when you... So the reason why you taste is because molecules from the food you're eating reach your tongue receptors. There's neurons in your tongue that can receive those molecules, and those senses get sent to your brain. And your brain is what produces your sense of taste. Your brain is what produces all your senses. Ears, there's neurons in your ears that observe the vibrations of air, and that gets sent to your brain in the form of electrochemical signals sent to your brain. Your sight, how you see, is not because your eyes, but because of the light goes into your eyes and filters into your brain. Your brain is what sees reality, not your eyes. Your eyes don't see; they only filter in the light to your brain. Your smell as well. There are neurons in your nose up here where molecules of air go into your nose and they disturb the neurons and they produce electrochemical signals that get sent to your brain. Your brain is what maps out your reality. Your brain is what generates the map of the world around you. That's how you see and observe. That's why you're conscious, because of your brain and all of your sensory systems. But in space, there's nothing to smell. There's nothing to taste. There's nothing there. It's just space. It's a quite different world than we are in. How do blind people perceive the world? Well, being blind is like seeing with your ears, right? We will never be able to perceive it, but I'll never be able to describe it to you in words. But the best way I can describe it is like seeing with your ears. What do your ears see? Nothing, right? There's nothing to see with that. There's no medium with which to see. The same with blind people. You don't see anything. There's nothing to see with. You don't see darkness. When you're blind, you don't even see darkness. You see nothing at all. You see what your ears see. And your other senses override your sight. Right? You have a more pronounced sense of taste and smell, things like that. Typically. Aren't neurons only in your brain and spine? No, you have neurons all over your body, even in your stomach. You have neurons. You have neurons in your stomach, in your ears, your nose, your mouth. Those are called nerves. Well, no, yes, you have nerves there too, but neurons. I'm not saying millions. Just maybe a few hundred neurons near those areas. Are memories just chemical reactions? Memories are when your brain... So when you have a memory, certain neurons in your brain light up, right? There's a certain pattern of neurons. When you're stimulated by a taste or a smell or a sound, certain neurons in the brain are stimulated. They light up. And that's how memories are stored. Because the next time you are stimulated in that same way, right? The next time you hear that sound or something similar to that sound, those same neurons glow up. Those same neurons. The same pattern of neurons light up. That's a memory. So memories are stored in the patterns of neurons that are lighting up when you are stimulated by things in your environment. That's a very basic level understanding of it. There's much more to it. Please, guys, there's much more. I'm not a scientist, but the point is, basically speaking, that's how memory works. Your brain has a way of recognizing or funneling certain patterns in neurons to light up, given certain simulations. What is string theory? String theory is a very basic understanding. It says that on the fundamental level, there's something deeper than quarks. There's something deeper than atoms, and that is a vibrating one-dimensional string of energy, and certain vibrations of energy yield certain particles, right? Certain frequencies of vibrations yield certain particles, and these vibrations could be strings, they could be two-dimensional objects, something fundamental. And from this, all particles are yielded. All particles emerge. Perhaps even gravity emerges from this. So the point is that it's a very fundamental understanding of how the universe works. Deeper than particle physics. Deeper than relativity. Is evolution smart? No, evolution does not care. There is no agency. There's nobody deciding what evolves or what doesn't. It seems like it. It seems like evolution is smart because it seems like there's something advancing. But that's not how evolution works. Evolution doesn't care if you get smarter. It cares if you can survive. We evolve according to the environment, the pressures that we experience. And if you can survive the pressures, you advance. That's it. There's nobody deciding how we evolve. It's just nature. It's amazing. It's remarkable. It's incredible. But it's just nature. And nature's incredible. There doesn't have to be a God. In fact, God is even more ridiculous than nature. It's like even less beautiful than nature. Explain Bluetooth. Bluetooth is just radio transmission, just radio waves that are sent from other things. They get sent to your phone, and your phone is able to perceive these signals and convert them into digital code that your phone then converts into images and sounds. Wi-Fi, Bluetooth, it's all the same shit. It's just radio waves, right, that can hold information because of the certain frequencies and wavelengths, right? Depending on the frequency of the wave, it tells your phone to act in certain ways and to produce certain code that then can be converted into images and things that you observe on your operating system. That's all. Will religions disappear eventually? No. Religion will always be here. And that's okay. And that's good. I'm happy about that. Religion isn't bad. Religion is a beautiful thing for people. You know, it's an imagination. It's a person's imagination. It's a person's ability to imagine and feel. But religion as we know it will fade away. Yes. Christianity and Islam will go away. Yes. Just like every religion does. But there will be new religions that emerge in our future. And that's okay. It's a human thing to do. Religion is a very human thing to do. We're always going to imagine. We're always going to speculate. We're always going to have these crazy, wacky ideas. It's always going to happen. But what I'm against is bad beliefs, bigoted ideas, hateful ideas. That's what I'm against. That's why I'm anti-theist. I'm not anti-religion. I'm anti-theistic. Will we ever time travel? Well, we know that if you travel fast enough through space, time slows down for you. In a sense, we can already time travel to the future by traveling fast. The faster you go through space, the slower time moves for you. If I were to go into a rocket ship in space at, say, half the speed of light, time for me would pass for maybe a month. But on the Earth, a year passed on the Earth. So if I go into space very quickly with the rocket ship and I come back to Earth a month later, only a month passed for me, but a year passed for the Earth. So in that sense, you can time travel because it's like a loophole, right? In space-time, you're going through a loophole. And the faster you go through space, the slower and slower time goes for you relative to the Earth. There's a calculation for this. You can calculate this, actually. It's remarkable. In fact, you can calculate how far into the future you want to go. But there's a limit to that. I can't travel faster than the speed of light. So in terms of like Back to the Future time travel, where you just pick a time in a car and you go there, that's probably not going to be possible. That is a different story. But I do have a documentary on my YouTube channel where it talks about time travel in good detail. You guys should go watch that. I don't know all the deals. I'm not a physicist. But all I can tell you is that, yes, there are some ways in which time travel is possible. Why is the Earth round? Okay, a lot of people are curious as to a lot of people are curious as to how we know the Earth is round. Well, very simple. It's geometry. It's basic geometry. So, a guy named Eratosthenes, he was a Greek mathematician about 2,000 years ago. He came up with this idea. He realized that in one latitude of the Earth, right, one place on the Earth, there was a certain shadow on a building, casted off of a building at a particular time of the day, right? At noon, the shadow was this long. But he also noticed that at the same time of the day, on a different latitude of the Earth, right, a more northern latitude, the shadow was a different size. At the same time of day. How could that be? How could it be that the shadows of two objects are different sizes? How could it be? Well, it's called geometry. Or he realized that the reason why he measured the distance between these two places, he measured the shadows of the sticks and used the Pythagorean theorem, and he realized that the Earth's got to be curved. There's got to be curvature to explain the differences in the shadows at the same time of day. He realized that the sun rays that come in straight forward to the Earth, there's got to be a curvature because of the angles at which the shadows are existing, and that's very simple mathematics, right? All you need, and you can actually measure, you can extrapolate this information by understanding the entire circumference of the Earth. And he actually calculated the circumference with like a 1% degree error. Very, very good. He was amazingly good. And he did this 2,000 years ago. Very simple calculation with geometry. That's how you figure it out. All you need is two sticks and the simple geometry, and you can tell the Earth is a sphere. Did that make it better for you guys? Did you guys understand that? What is space made of? That whole planets and galaxies. Space isn't made. We don't know what a space is made of. We don't know. It seems to be that space is made up of vibrations of energy, quantum fields, but we don't know. We don't know. That's a great question. We don't know. Was Interstellar ahead of its time? Sure, I guess you can say that. How did Copernicus figure out that we are heliocentric? I think he was looking at eclipses, I believe. I forgot actually. That's a good question. I think he was looking at Mercury's retrograde, and yeah, he was looking at the retrograde, and he was like, "Why do certain planets seem to be moving slower in certain times, or backwards?" And he realized that we are moving around the sun. That's why. But yeah, just think about it. 1,000 years ago, people didn't even know that the sun was the center of the solar system. We know so much today versus 1,000 years ago, let alone 10,000 years ago. Think of all of our ancestors who looked up at the sky and didn't know what they were looking at. They didn't know that stars were suns far away. They didn't know that the moon was another planet or another rock like the Earth. They didn't even know that the Earth was a rock. They didn't know what a galaxy was. They didn't know what black holes were. They didn't know what anything was. So we should be grateful that we're here in this time, able to understand a lot of things about the world. Hey Jasmine, check your Snapchat. I sent you a couple messages on Snap. I'd love for you to respond. We have evolved a lot. Well, yes, we've evolved biologically, but also mentally, yes. We are in an amazing time. We are in an amazing time today. Could we breathe on Mars eventually? No. You can't. You would not survive on breathing on Mars right now. You would die within 10 seconds. But perhaps in the future, we would. Yes, it's possible that in the future, if we bring enough oxygen there and bring enough stuff there, enough gases, you can make Mars breathable. It's possible, but it's difficult because Mars has no magnetic field, and that's a big challenge. It's also a challenge because it's low gravity. The atmosphere is going to be harder to maintain. But it's possible. It is possible that one day we will be able to breathe and live on the surface of Mars. Very possible. That's why I see it. That's why I'm saying Mars is our best bet at a second Earth. Are we able to make a magnetic field for Mars? So, I have a video on my main channel where I talk about this. And, yes, it actually is possible. Very difficult, though. And what we need is... What you would need is a long tube that stretches the entire planet. A long tube that magnetically interacts with itself. A long tube. It would have to produce currents, electrical currents, and that's what magnetic fields really. It's what electricity is related to magnetism. It's really just magnetism with motion. So, if you can develop a tube of electric currents around Mars, you can actually develop a magnetic field, a small one. And it's possible, but very difficult to do. Is Mars nuking? Is Mars planning to nuke both poles of Mars to make it produce heat? Valid. Yes. Yeah, absolutely. But again, nuking Mars would only have a very small impact on the temperature. It might raise the temperature maybe 1 or 2 degrees. Right? We needed to raise like 100 degrees. We need way more temperature rise on Mars. Nuking will work only to a small degree though. We need a lot of energy. We need a lot more energy on Mars. Some people say lasers, beaming lasers down. Some people say solar mirrors. There's many different methods, but we need lots of energy on Mars to make it warmer. All right, guys. Well, that's all for today. Thanks for being here. Hope you learned something. So my favorite nebula, Orion. I love Orion. Very beautiful. I'll just show you guys this. By the way, everybody go follow my YouTube. Please follow my YouTube. There it is. Gorgeous. This is from NASA's Hubble telescope. Close my tabs. Yeah, well, I bought the computer for this reason. That's why I bought this computer. It has 32 gigs of RAM. But it's a very beautiful nebula. It's 1,000 light years away. It's 24 light years across. So. $32 gigs of DDR4 RAM, yeah. Well, it's overclocked. I think it's like 3,300 megahertz. Plus, I got an Intel 13 Gen. How long will Voyager 1 and 2 survive? They will survive for perhaps 1 billion years. It is very unlikely that they'll ever hit something. So there's so much space in the solar system that they'll probably, or in the Milky Way galaxy, that they'll likely never hit anything. Ever. Maybe one day an alien will pick it up and find stuff on it. On Voyager's spacecraft, which are floating now in interstellar space, they just passed the heliosphere. They're now in interstellar space. But on these spacecraft are discs of Earth photos and Earth sounds and Earth music and all about humans and all about animals. And there's a lot of amazing stuff on these spacecraft that was intended to be there in case aliens picked up one day. Imagine one day aliens pick up that disc and read it and visit the Earth, pay a visit to the Earth. That'd be amazing. One of the greatest things we could do is find life, discover another species. But either way, either whether or not we're alone, both results will be amazing, right? If there are other aliens out there, that would be amazing to understand how they got there, how they evolved. What are they made of? What's their story? How do they think? What's their religion like? What is their thought processes like? What do they like to do? What are their goals, right? What's their technology like? That would be amazing to understand. And if we are alone, if we really are the only ones in the universe, that would place more importance on ourselves, more importance on who we are, and to preserve Earth, to preserve this life, this alone, how amazing we would be. How precious and valuable we would be if we were the only ones in the universe. So either way, we win. But that's all up to us. I'll leave on this, but this is the last thing I'll leave on. But this is one of the greatest photos in the history of the Earth we've ever taken, called the pale blue dot. Do you guys see? Do you guys see this? Hold on. Do you guys see this? Right there. See that dot? You can see a very, very faint dot. If you look closely enough, you'll see it. Very, very faint dot. Well, that's our planet. That's the Earth. That is the Earth from 4 billion miles away. Right? That's the entire planet. That's everything you've ever seen, everybody you've ever known. Every person in the world, every war, every king, every peasant, everyone that's ever loved anybody, every animal, everything that's ever happened on that dot. Against this backdrop of darkness and void, right? Look at this. Space. Emptiness. Look at how amazing that is. You know, look at that puts things in perspective. At how precious we are, how small we are relative to things. We have to take care of the planet. We have to do good. Let's treat each other better. Let's cherish this pale blue dot. The only one we know we have. The only home we have. Life is amazing. Don't waste it. Do something. Be useful. Let's change the world. So today we went over the history of our planet. We went over how we got here, our journey, and now here we are, right? Now it's the present time, and look at what we can do. Look at what we've done. Look at where we can go, right? We're in an amazing time where we have choices, and our choices that we make today can make our future better or worse. It's up to us.